Hello, everyone. I'm glad you're here. Uh, we're going to explore FM synthesis, but we're going to look at it perhaps from a new perspective, one that you might not have considered before, or at least one that I haven't seen elsewhere. So last year, I was here presenting, and I didn't have a slide introducing myself. So this year, I made a Twitter account. 2 months later, Twitter imploded. You can blame me for that. Okay, so here's what we're going to do. First, we're going to go through what other tutorials to FM synthesis do. Then we're going to explore perhaps some of the math that they don't want you to know. There will be some code. We'll explore the differences between linear, exponential, and through zero frequency modulation. We'll see some examples of digital synthesizers that use FM synthesis. We'll also look at analog FM and how it's implemented. And finally, we are going to find a new way to conduct FM synthesis. So let's go. Okay, so if you go into YouTube and you type FM synthesis tutorial, this is going to come up. There will usually be some person that will tell you that they will have an LFO modulating the pitch of an oscillator, usually. I've seen a ton of these tutorials, so they're all the same. Just watch one. And they will tell you that this is vibrato. Then they tell you that if we increase the frequency of the LFO that's modulating the signal, that is audio rate vibrato. That's FM, if you increase it at audio frequencies. Then usually they will start mentioning Yamaha and their nomenclature with the carriers and the modulators and the operators and all that. But that's a bit tangential to our discussion here. Then they will introduce the algorithm, which are the different ways to route the modulators and to the carriers. For example, you can have a modulator modulating another modulator that in turn modulates a carrier. And they will usually at the end they get into feedback, which is when the last or maybe some middle stage goes back and modulates itself. And they will also introduce harmonic and inharmonic ratios between the oscillators that make different sounds. And some of them also explain the difference between linear and exponential FM, but not all of them. Okay, so, these are the, if you are an FM user, these are the basic rules you might have heard about FM synthesis and how to use it if you don't know how it works. So they will tell you for musical results, these are the basic rules you need to follow. Use basic waves, maybe sines. Use low ratios, because if you increase the ratio too much, it becomes basically noise, and we'll see why that happens. And they will tell you not to add too many modulators or large amounts of modulation in general. And they will tell you that the use cases for FM, once you start ramping up the ratios, that it produces inharmonic sounds that are metallic and they're good for simulating bells or keys. But it can also be good for basses if you add an envelope to the modulator and decrease it very slowly. It's a nice bass sound. Yeah. So we are developers. We need something a little deeper than the users. So we need to look at the math and, more importantly, how it applies to practice. We need the comprehensive theory of FM. And at this stage, it's easier to consider phase modulation. Now, originally, this is what Yamaha did, and they called it frequency modulation, but internally it was implemented as phase modulation, and we'll see if they're equivalent or not. We're going to explore the relationship between PM and FM and discover a new way to extend it. So yeah, this is the math. It's a little boring, doesn't have much to say. You put a signal inside another signal, and you can change the phase, which is which part of the waveform, assuming it's cyclical, you're reading from. We also define a phase modulation index. Okay, these are details. And we can also phase modulate any signal that comes in. So it doesn't have to be a sine, assuming you can add a variable delay inside the assuming you can index with a variable delay into the signal, then we can phase modulate it. For example, we can have synthesis, we can have wavetables. So aliasing, typically the FM sound is defined by aliasing, because once you start increasing the frequency, the ratios, and you start adding extra modulation, you get aliasing. Now, this is defined by reflection around the Nyquist limit. So, for example, let's say we have, no, there's a mistake there that the Nyquist limit, like the sample rates would be double that. Yeah, I should correct that. But anyway, yeah, so the assuming we have this signal at 18 kilohertz, it's modulated by a signal at 6 kilohertz, both are sines. So we have two sidebands, so the lower sideband and the upper sideband, and the upper sideband increases above the Nyquist limit. Again, the Nyquist limit is 22.5, and the sample rate is actually 41. So yeah, well, we get reflection around the Nyquist limit, and the upper sideband reflects down, and generally this is not going to be harmonic with the lower sideband, so it's going to produce something that sounds metallic or noisy at very high rates, or it will not necessarily sound nice. So that might be the case, but as it turns out, aliasing is part of the FM sound. So if you have an older FM synth and you try to load the presets and you try to remove the aliasing, it's not going to sound the same. So what we know as FM, which is actually PM, includes this aliasing. Yeah, and this is exactly why we use it for noise. Yeah, so again, the math for frequency modulation, same thing, except this time, instead of modulating the phase, we're modulating the frequency of an oscillator, and again, for simplicity, we're using sines, but then we're going to see that can be any waveform. So we have our modulator M, and yeah, the interesting case here is that there's an integral that appears inside the expression. We can also define the frequency deviation, F delta, and when it comes to the FM signals, the resulting spectrum, actually extends to infinity. Typically, when we try to describe it, we might say that most of it is within a certain frequency range, but we know that it's implied that it goes to infinity. So actually, if we want to represent it, we need to have an infinite sample rate, or at least very large sample rate that doesn't matter, or we're going to get reflections. Yeah, so assuming we have, in the easy case, we have a sine that's modulating another sine, so we can insert the modulating signal into the expression, and for a sinusoidal modulator, its integral is also sinusoidal. So this is the easy case, and we can simplify the expression, and we have this result. We can also define the frequency deviation that depends on the amplitude of the modulator. And also, since this is a good case, we also have an analytic solution that involves Bessel functions. You can look this up. I will not bore you anymore. So what happens in the case that we have a non-sinusoidal modulator? Well, we still have an integral in there, but this time we cannot compute it as easily. So the best explanation I found, the bounds that we can have, is that most of the power is within a certain bandwidth, including this deviation ratio that is, I believe it's the amplitude of the modulator divided by the deviation frequency, something like that. You can look it up. Yeah. But even that extends to infinity, actually. And we don't have an analytic solution in the general case that we can describe the signal. So we can also apply frequency modulation to a general signal, assuming we can change its frequency. So if it's something we are generating, or perhaps via wavetables or samples or synthesis in general, we can change the frequency of our oscillator, so we can frequency modulate it. But we cannot do that for an arbitrary input. So if someone gives us a signal and says, hey, can you frequency modulate that? Well, we would need a center frequency in order to modulate around it. And it doesn't necessarily have a main frequency. It would be white noise. So linear versus exponential FM, again, this is usually featured in other tutorials, but I'll cover it for completeness. So in linear FM, we have linear modulation around the center frequency. So it's plus or minus 100 in this case. So human hearing is, as you know, logarithmic. So we can perceive sound in octaves, and we have this doubling of frequency in each octave. So the average frequency, which is how we perceive it, for linear FM would be the center frequency, but the perceived frequency for exponential FM is something different, and we hear it as drifting. So exponential FM sounds like it's drifting in frequency. And there are ways to correct it. We found some AC coupled FM. And this is also this also drifts for linear FM if there is a DC component. So a special type of FM is through zero frequency modulation. It is most commonly associated with analog oscillators, which if you look up a design for an oscillator, unless it's designed for it, it will not go below 0 Hertz. It will just stop. So There are some VCOs that are designed to reverse phase. Usually, they're found in Eurorack modules, or they have. What happens is when they go below 0 Hertz, they increase frequency in reverse, so the waveform flips around. So it sounds like linear FM, and you can modulate it more before it starts producing a harmonic sound. And here we see an example. This is the Doepfer quadrature through 0 VCO that is one of the modules that actually has through 0 capability. So what is the relationship between frequency modulation and phase modulation? This is the equation that we have for phase modulation. And if we notice something, we have this modulator in there, but no one tells us how to group it. So we can pick the top grouping, which is phase modulation, but we can also pick a different grouping that says, okay, what if we take this same modulator and instead of associating it with a phase, we associate it with a frequency. Again, same exact expression, sounds the same, just a different way to look at it. So what happens is that it looks like FM because there is a signal that is modulating the frequency of the carrier. And a useful insight at this stage is that carrier frequency modulation is the time derivative of the phase modulation. Or we can define that the phase modulation is the integral of the carrier frequency modulation. So how are we going to hear PM? Again, I'm assuming at this stage that we have slightly higher ratio and slightly higher amplitude in our modulators. So we're in the case where this applies. So we cannot hear the phase directly, but we can hear frequencies. So when we have a PM signal, what we actually hear is FM with the derivative of the PM signal. So with the derivative of the modulator. And this is an important insight here. Because, as we said, they're both equivalent, and this is why Yamaha marketed that as frequency modulation. We see that, at least in the sinusoidal case, it's the same, and it's also similar here. Let's consider the case where we have the phase modulation of a sine wave with a triangular waveform, so it goes. So the derivative, which is the slope, is a positive constant, then a negative constant, and it repeats. So we would hear it as frequency modulation. We would hear the center frequency plus some offset, and the center frequency minus some offset. So I also put some explanations here about related topics like ring modulation, which is when you multiply the carrier and the modulator together. There is not much to say here. Basically what happens is you get the sum and the difference of the frequencies, but not the frequencies themselves. So as a sound, you would describe it as robotic. It's good for special effects, mostly. So if you do this with arbitrary waveforms, you have a multiplication here in time, so it ends up as a convolution in frequencies, and harmonic inputs can still produce somewhat harmonic output. Yeah, so another related topic is amplitude modulation, or AM, which is when we change the amplitude of our signal with our modulator. And we can see how this looks similar to the other. It looks similar to ring modulation, but there is an offset in the time domain. We can also define the AM modulation index with this expression. And we can also see that the spectrum of the signal is predictable if we have a sign as a carrier. So if the modulator is also a sign, then we get the sidebands. So the frequency is repeated at an offset of the center frequency plus an offset by the modulating frequency, and the same frequency minus the modulating frequency. For a different signal, let's say we have an arbitrary non-sinusoidal modulator and a sinusoidal carrier, we still get the unchanged carrier, but we also get the entire frequency spectrum repeating. So rather than 2 repeats at the frequency spectrum, we get the entire spectrum of the modulator. So let's look at a code example for FM. Now, this is what I found. It's not the best for educational purposes, I recognize it. But it's coming from a production database. This is the search synth, the FM2 oscillator, and I think they also have some oscillators that deliberately include aliasing. So this is the topic we talked about before. This includes a lot of extra things that we don't care about at this stage, but you might want to look into, for example, modulation depth, feedback, and relative modulators. And there are also some parameters that come in, but basically the only important thing here is the first line, which is a phase accumulator. So we advance the phase depending on our frequencies, and this is frequency modulation. And we also have to remember to wrap the phase. Okay, it's time to look at some examples of FM synthesizers. There is phase plan by kilohertz. It also has different methods of synthesis, but you can also do FM, PM, all of the related methods. There is flow motion by waves, and the thing I want to highlight, I just saw an interview that they deliberately limit the amount of modulation that you do in order to keep things interesting, because there is, if you have a parameter that goes from 0 to 100, but the range from, say, 10 to 100 is all noise, there's no difference between noise and more noise. You're not going to get any particular insight from that. And I think that was very clever, actually, that they recognized it and they did that. Yeah, there is also Citrus by ImageLine. This one, it has FM, which is actually PM, and I believe RM. There is the Dext, which is an emulation of the original Yamaha DX7, the first FM, but actually PM synth. And can also load the presets from the original device, if you have them. There's also FM8 by Native Instruments, which again, it can load the presets, but what you're going to notice is that each of these has different parameter ranges. So what might be 0 to 100 on one synth might be, I don't know, 0 to 5 on another, or some ratio. You can find on the internet different tables that have the mapping between the parameter ranges. So if you want to translate the patches from one synth to another, you would have to go through the and translate the ranges, but just the mechanical step, so you can do it. Yeah, and there is also Ableton operator there, which has many different waveforms as carriers and modulators. Okay, so let's look at analog FM. once again. What we can consider here is that analog synths don't implement frequency modulation with phase modulation like digital synths do. Mostly, again, this is not always the case, but some of the examples we've seen do that. So instead, they use voltage-controlled oscillators, which are, of course, implemented in hardware with resistors and op-amps. So these don't have aliasing exactly, but of course, as actual devices, the VCOs have their own limitations, and this will be reflected in the FM signal. So usually, if you go in forums, you're going to find that people say that analog FM sounds different than digital FM, and of course, this makes sense because it's an analog oscillator. It's going to have some variations or other effects. So if you want to make this kind of FM, you would need to simulate the circuit that has the oscillator, and then you would use the same method in order to have a similar sound. I don't think you can get exact. You would also have to use a very high sample rate if you don't want to have problems. And this is the point where perhaps it becomes impractical to simulate it. And again, some Eurorack modules, or perhaps most of them, have analog FM, which is their frequency control input. You can put the jack and modulate it that way. Yeah, so enough FM. I think at this stage you've had enough, right? No? You want more? Okay, there's more at the end. Okay, let's talk about filters. Okay, so in hardware, we have this active filter. So we can make an active, in this case it's inverting, but we don't care, low-pass filter, which is created with an op-amp integrator. And in this case, the output voltage is proportional to the negative, but again, we don't really care about that, integral of the input voltage. We can also define a differentiator, which is the active high-pass filter. In this case, the output voltage is proportional to the input voltage rate of change. Yeah, so these circuits implement the mathematical operations of integration and differentiation in hardware. And as filters, they can give us 6 dB per octave of filtering per stage, and we can cascade them. For example, if we put 2 of them in a row, we get 12 dB per octave. Nothing new here. So these are the circuits. We see the low-pass behavior of the op-amp integrator. And again, there's some extra stuff, but don't worry about that. And the differentiator is the opposite thing. It acts as a high-pass filter. Yeah. So what if we want a different filter slope than 6 dB per octave? For example, I found this recent post in a forum, or some, again, Discord posts that they demonstrate that clearly this is something that people want, right? If they're writing, how can we do that? So, as an aside, after I prepared my talk, I found out that some companies also have fractional filters, but they don't use this method. So that's interesting, and I want to learn how it ties into it. Perhaps there is a unifying theory to be made, but what we're going to explore here is different. Yeah, so imagine we had a special supercapacitor that allowed us to implement fractional derivatives of any order rather than the first order. So then we could just take this magical device, we put it into our integrator or differentiator instead of a normal capacitor, and ta-da, we have the variable order filters. We can have any filter we want. That's it. Any questions? Okay, there's more. Okay. Okay, but where are we going to get this magical device? Can we go to Mauser, type in fractional capacitor, and order one? Well, no, but turns out we can do something about that. So we can implement one of these as an active device using transistors and op-amps. Have any of you seen this before? No? Okay, this is new. Good. It started to get boring. So you can make it, but you would have to use many transistors just to make a single fractional capacitor. So for example, each of these devices is an OTA. No, it's actually a controlled resistor, but uses an OTA internally, and then each OTA uses more than 10 transistors, so you would need 200 or 300 transistors to implement the structure, but you can do it. So what this implements is a fifth order, a continued fraction expansion, so it's not the actual fractional derivative, but it's a good enough approximation in the, I think, 10 hertz to 100 kilohertz, which is good enough for audio. Yeah, you can see the paper I linked at the end for more of this if you're interested. But when it comes to simulations, we don't really care about the physical implementation. We only need a way to have a fractional derivative, right? So at this stage, I want to have a pause and disambiguate between the, let's say, the special half capacitor and the capacitor that has half the value. So what a capacitor with half the value is, it changes the cutoff frequency of our filter. But what the fractional capacitor, this magical device, does is it controls the slope of the filter. So for example, let's say we have this filter here. We can either change the value of the capacitor, go to Mauser, buy a new one, and change the cutoff of our filter, or we can replace it with the fractional capacitor, in which case we get the different behavior. Yeah. I would like to thank the person that made those sketches, not me. Yeah, so, okay, let's get into the math. What is the meaning of a fractional derivative? How many of you know fractional calculus here? Okay, few people, maybe. Okay, yeah, I'm not a mathematician, I'm an engineer. So this is going to get a little hand-wavy, perhaps. I apologize for that. But let's start with the easy case. We have polynomials, in which case we can easily differentiate them. Nothing new here. But we can also imagine that there is a continuous derivative operator that interpolates between these functions. So for example, we can have the square root, which is the half power, and that is a fractional derivative. No, not a fractional derivative. I mean, it's in between the polynomials that come from this differentiation, so perhaps we can define an operator to get it. Yeah, so the challenge comes when we try to apply this to different non-polynomial functions, for example, sine waves, or exponentials, or any other function, really. So in order to define this operator, we need to take a step back and look at what should this fractional derivative have. First of all, nice thing to have would be to be able to compose this fractional derivative with itself. For example, if you apply the if you multiply the square root of a number twice, then that is multiplication by the number. And we want to extend that, and we want our fractional derivative, if we take the half derivative twice, we should ideally get the regular derivative that we know, right? And again, we can compose them in many different ways. For example, we can have 1/3 derivatives that we need to compose 3 of them in order to get the regular one. Yeah, so it turns out that some mathematicians have thought about this problem for longer than we have, and they figured out that somehow it's easier to do the inverse and solve this by going through fractional integrals. Now, I know what you're thinking, that aren't integrals harder than derivatives? Well, turns out in this case that we can integrate any continuous function, but differentiation is, of course, a local operation. So if there are discontinuities, we can do that. And another nice property of integrals is that we can compose them. We can put an integral inside an integral. And we can, of course, define a fractional integral to have these properties. And there's an excellent explanation video that I will link at the end. So, integral, or the opposite operation of the derivative, or the antiderivative. So, we want, if integrals and derivatives cancel out, we can apply a derivative and an integral, and we get the function back. We can use this property of cancellation to derive a fractional derivative of any order that we want. For example, this is one definition of fractional derivative. There are many definitions. So here we have an integer derivative, that is this one here, that is applied after an integral that could be of any order, even fractional, to get our fractional derivative. So as an example, let's say that this is an integral of order 1.5, and this is regular derivative. That means we can have a half derivative, or a derivative of order 0.5, right? Makes sense. I'm getting some confused looks here. Okay. There will be time for questions, I hope. Okay, so if the definition of fractional derivatives comes from integrals, there are some interesting properties that we can observe. So fractional derivatives are non-local, same as integrals, which means they extend at a range, right? The integration limits. And it turns out in this case, the integration limits matter for our definition of a fractional derivative operator. But it turns out that somehow the fractional derivative operator becomes local when the order of the fractional derivative is an integer. So if it's 0.99, it's not local. But if it's 1, it's local. I don't know how it works. You have to ask a mathematician. Yeah, and of course, we can also compose two non-local functions to get a local function, which again sounds a bit weird, but can happen. And as far as I found, there is no agreed geometrical definition like there is for the Riemann intervals, where you separate it into slices and you can draw the slices. Yeah, another interesting property of this fractional capacitor is that it exhibits a memory effect. So that means that the state can also depend on what happened in the past. This is unlike a regular capacitor that we can define with a capacitance and a certain charge. So it doesn't need any memory in order to describe it, assuming it's ideal, of course. So the supercapacitor has memory, and I believe it also ties into this non-locality because it's an integral, but I can't prove it. Yeah. So it turns out that there are many definitions for the fractional derivative operator. We only saw one of them. You can apply them in different orders. So there is integration before differentiation, differentiation before integration, and there are many definitions that mathematicians have come up with, and they can all define the fractional derivative operator. And we have a library that supports many algorithms. I will see that later. So this is the new thing. Fractional frequency modulation. If Fm is the first derivative of phase modulation, what about all the other derivatives that we just defined? So can we have a half derivative of phase modulation? And if we do, then what does it mean? That's fractional frequency modulation. And it's an idea to smoothly morph between phase modulation and frequency modulation, or even beyond with a knob. So it can also be defined for non-sinusoidal waveforms, for integrals. And yeah, there are some limitations that you have to consider, but in general, you can do it. So as some of you know already, I'm using Julia for simulating circuits. There's a talk on YouTube that you can find. But in this case, we are mostly interested in fractional diffq.jl, which is a library for solving fractional differential equations. So if we define our problem as a fractional differential equation, then we can do fractional FM synthesis. So this is the carrier here, the third one. I added some offset, just some random thing for plotting, doesn't matter. We also have its phase, that's right here. It increases linearly with time. And this is the modulator, and it also increases linearly with time, the phase, I mean. And this is the modulator going inside the carrier and with fractional order. So in order to, so the way this library works is we have to describe what we want as with the derivatives. So if we want to define a sign, we use a cosine, which is its derivative, the first derivative. And if we want to define a cosine, we have its derivative, which is the minus sign. But those are all details. You can replace this with your own waveforms or anything, really, even, I don't know, audio input. So yeah, this is where we define the fractional derivative order. So this one should be 0.5. And yes, Julia supports Unicode. This is a Greek alpha. Yeah, so the rest of the stuff is just how to use the library. Thing I want to note is that here you can choose the algorithm that is being used. So you have the different, the Caputo fractional derivative and the Riemann-Liouville fractional derivative and all of the, well, not all of them, but some of the others that we talked about. So this is another interesting area to experiment. So this is what it does. So this is the first derivative, which has an order of 1. Then we define a fractional derivative. There's also an offset that I noticed. I don't know why this happens, but I believe it ties either into the initial values, this is my hypothesis, or perhaps into the non-locality with the previous history of the system mattering. So what you use as your initial value matters in this case. And we can see that the shape changes here of the carrier. And then we can see that if we decrease the order further, we get this slightly jagged waveform. And you can play with this. You can add different waveforms, different orders. Unfortunately, I didn't export any audio demos, but the code runs, so you can take it and play with it. And perhaps there is a way to account for the DC offset that we see here. Yeah, perhaps a more solid implementation would look into that and whether it's actually something useful that we want for audio or whether it's it can be removed like the AC coupled version that we saw previously, where they just remove it. It's not useful for the sound. So yeah, what can we do in the future? We can perhaps explore real-time fractional frequency modulation synthesis. We can see how to control it with MIDI or another control signal. An interesting post that I saw, this came out a week ago or so, is that you can now export Julia programs to embedded platforms. Not all of them, actually. There's a subset of operations, and I don't think that the library I'm showcasing here is actually supported. So this is very new and experimental, but if you want to look into it, it's there. Yeah, and I was speaking with Zerent in the conference, and we had this this idea of applying anti-derivative, anti-aliasing to phase modulation. Because if you think about it, phase modulation is a modulated delay. And a delay, if you look at the PM signal, it looks like wave shaping the delay with using our input waveform X as a modulator, as a wave shaper. So there are a few details to consider, and we haven't tried it, but it should require the local integral. We can approximate it with a running sum. And another interesting idea is to experiment, again, with different waveforms, different orders, different fractional derivative operators, all that. And here you can see some of the resources that I used for this talk. The first one is an explanation of the active filters. This is a great paper. I believe I saw a previous version of this paper back in Greece. I think it was the same presenter, maybe I'm mistaken. But I'm linking this one. Yeah, there is this excellent video about fractional calculus, which I'm not an expert on by any means. And yeah, I'd like to thank the authors of this very helpful library. Signal Smith, who helped me with some of the diagrams in the slides, and the authors of the Sedge synthesizer. And there is a blog post that, the forum post, someone asked about the differences between the mapping ranges of the parameters. So that's it for today. Thank you for being here.